My name is Charlie Ray. Like you said, I'm an undergraduate from California Polytechnic State University in San Luis Obispo. And today, I'm just going to be talking about some research I did over the summer with Dr. John Clements and Dr. Ayaan Kazaruni about mutation testing in Racket. So kind of first up, what is mutation testing? Kind of the core idea behind it is you take some of your source code, you inject just a very small change into it. Kind of the idea behind that is if your source code is written in such a way that everything is purposeful, that small change will kind of break it in some way. So you have some source code, you have some test cases that initially all pass on that source code. You introduce your little bug or your little change, your mutant, and then kind of from there, two cases can arise. Either the first one, kind of some of your test cases fail, in which case you'd call the mutant killed, which is generally a good thing, because you have your test cases basically saying, this is a program that we think is broken, and we're failing to signify that. And then the other possibility is all of your test cases still pass, and we would call that mutant surviving. And that's generally not a great thing, because now we have this code which we think is broken, but we have test cases saying it looks good. So you don't really love that. And then there's kind of two other possibilities that could happen. Your mutant could time out, in which case, let's say the change you made kind of introduced an infinite loop within the program. Your test cases are never going to finish running. They're never going to pass. So sometimes those get looped into the killed mutants because your test cases didn't pass. They didn't finish running. And then the other last possibility is not covered. Usually mutation testing is kind of ran in parallel with something like line coverage. And if a mutant is generated on a line that isn't covered by your tests, obviously they're not going to catch it because they don't run those lines. So most mutation engines just won't even really run those mutants. It'll just continue on. And then kind of the metric that mutation analysis uses to kind of like provide a adequacy of your test cases is mutation score. And that's just the total number of killed mutants divided by the total number of mutants generated. So that's kind of the percentage of mutants that were killed. And usually mutation score corresponds with a higher test suite adequacy. And I should mention that mutation analysis is usually to test your test cases, not the program itself. Make sure your test cases are kind of enough. So just kind of a quick example of mutation testing in a Racket program. I have this kind of example function on the left. It just kind of takes some numbers and then outputs some numbers, and I have some test cases below it. And you can kind of verify that these test cases do get 100% line coverage on this code. However, when I mutate it by basically changing the second conditional, basically removing that by inserting a false where the a greater than 0 conditional is, all the test cases still pass. Although you might kind of notice that the first test case just doesn't really check for the functionality of the code. It just checks if it returns a real number, which is kind of like the whole point of mutation testing, is it kind of allows you to see if your test cases are actually testing the functionality of your code rather than just hitting some coverage metric. So I want to take some time to kind of talk about type of mutator, just so you get a little bit more of an idea of what mutation testing looks like. This one is called the arithmetic operator deletion mutator, and it just kind of operates on arithmetic functions. So addition, subtraction, multiplication, division, and modulo. And what it would do is basically, I'll just focus on the addition one, is it would take, basically you're adding two numbers, A and B. It would replace the whole addition expression with either A or B, and then run your test cases with that on there. And I say A or B, but really the mutation engine would generate two mutants, replace it with A, run the test cases, and then replace it with B, run the test cases again. And then obviously in Racket, you can have kind of an arbitrary number of operands. So something like the last example down here would generate 3 different mutants, so you'd run your test cases 3 individual times. So a little bit more on mutation testing. It's not necessarily new. It was originally proposed by D'Amelio in 1987. And like I said, it kind of requires a higher test suite adequacy than something like line coverage. So it's kind of its like core benefit. The core disadvantage of mutation testing, though, is it's very computationally expensive compared to something like line coverage. So for example, this little snippet just from an open source Racket project, basically each one of those red boxes is a place where a mutant might get generated by a mutation engine. So this one snippet, 11 lines of code, would generate 20 mutants, which would then correspond to running your test cases 20 different times, which, if you imagine it's a part of a larger project, could get very expensive very quickly. And then, like I said, mutation testing is not new, but it is a little bit new in Racket. So there is a more extensive body of research in mutation testing in Java. kind of analyzing PIT, which is the most popular Java mutation tool. And yeah. And then, so yeah, basically PIT offers a big list of mutators that you can choose from. And one way to kind of speed up mutation testing is just generating less mutants, so you run your test cases less times. So you just use fewer mutators. But that kind of brings up the question, like, which mutators should we choose? So Dr. Kozruni and his team in 2020 found that like a subset of mutators were able to predict the mutation score of the full set of mutators. And what I mean by that is basically you use all the mutators you can, you get a mutation score for some program, and then you choose a subset of the mutators and you run it on the same program, and those two mutators or mutation scores are generally pretty highly correlated. So you can predict kind of what mutation score you'd get from the full coverage while not really running all of the mutators on that. So this plot, I should explain why there's 4 subplots basically. They ran mutation analysis on a bunch of student submissions for a Racket course, or not a Racket course, a Java course, and then grouped them kind of by submission size. So as you move farther to the right, the projects tend to get bigger and more complex. And then the kind of brown boxes are the number of mutants generated. And you can see that drops off quite significantly as we reduce the number of mutators that we use. And then the blue line is the kind of accuracy that those subsets have in predicting the mutation score of like the full set of mutators. So you can kind of see that we do end up getting a pretty significant speed up in time while not losing too much accuracy as a mutation analysis tool. And then additionally, they kind of wanted to push it and see how far they could go. So they found that a subset of the deletion set, which was the smallest subset on the last slide, was kind of able to still have high enough accuracy in predicting the full coverage when compared to something like a one operator thing. So this is just another very similar plot. And they did a forward selection to kind of find what 2 mutators were the most valuable to use. And what they found was that remove conditionals was kind of the most valuable mutator, all in all. And then arithmetic operator deletion, the one that we looked at before, if we pair it with remove conditionals, you get a pretty high accuracy in predicting the mutation score of the full set of mutators. So that kind of brings me back to kind of the work that I did this summer. And I extended Lukas Lazarek's mutate library. I believe he did a talk at RacketCon, I think last year, to include the remove conditionals and arithmetic operator deletion mutators, just because we wanted to see if those were useful within Racket. So what we did is we ran mutation analysis on both student submissions and open source Racket projects. And then we kind of wanted to answer the question if, are those mutators useful for evaluating test suite adequacy within Racket? And then would it be beneficial for students kind of above line coverage? And then also as a kind of a sub-question, we wanted to ask is, do our results align with Kozruni's findings in Java? Is remove conditionals kind of the most important mutator that we test? I've talked about it a lot, but I kind of want to give you an example of remove conditionals. It kind of operates on these Boolean statements. So for example, it will mutate an AND statement. If you have 3 conditionals, the AND to false mutator at least will insert a false kind of at every possible location it could. So an AND with 3 conditionals kind of nested within it will generate 3 mutants, and a false will go every place it could. And then there's the AND to true, which does a very similar thing, except instead of false, it just replaces it with true. And then there's also an OR to false, which basically the same thing, but it just operates on the OR function rather than the AND function. And then OR to true, very similar thing. There is a if to false, where basically you have a if test, and then you just mutate the test to false, so you force the else branch to run. And then you have a to true, where you force the then branch to run. And then there's 2 more that kind of align closely with PIT. There's the con to false and con to true. Hopefully these are pretty self-explanatory now. Basically, you have a con with a bunch of tests. You just replace the tests with a false each place it could go. So with 3 tests, I would create 3 mutants. And I just kind of exclude those branches to running. And then the con to true, I would once again kind of force a branch to run by mutating it to a true. And then there's one that I kind of decided to add into the Racket mutator that doesn't really exist in Java, just because Java doesn't have really like a match statement. But I kind of found that a lot of people and a lot of students were using match as kind of a Boolean flow operator. So basically what the match removal will do, it'll take a pattern and just kind of remove it from existence from the code. So it'll just remove that branch from ever trying to run. And that's what the match removal does. So like I said, we ran this on student submissions. These student submissions were required to have 100% line coverage. So they all did. There was 553 of them, and they were the projects were for a programming languages class based on the text programming languages, applications, and interpretation by Shriram Krishnamurti. So the students had to develop a parser and interpreter for a made-up language. I'm sure you guys kind of have a general idea of what that might look like. So that kind of was high amounts of recursion and match-based branching, which was one of the reasons for the match removal mutator. And then the open source Racket projects, we scraped and processed coverage data from 354 open source projects from the Racket package index. And then we actually decided to run mutation testing on 55 of those. Yes. But yeah, so on 55 of those, which met our coverage and like requirements, just kind of like I said, mutation testing doesn't really make a whole lot of sense with a project with low amounts of coverage. So we set our cutoff at 90%, and then we wanted to have just enough mutants of those projects. We set our length cutoff at 1,000 lines of code. And before I kind of, because there might be a lot of people here who work with these open source projects or maybe use them, here's just the kind of list of all 55 of them. You can kind of try to look at them, see if you recognize any.
Can I see the results from that?
Mm-hmm. Yeah, I can definitely share the results at some point. But yeah, so yeah, before I kind of talk about the high-level results, I do want to kind of talk about kind of different types of the mutants. So there's, and kind of try to convince you that mutation testing is actually useful for Racket projects. So there's kind of two types of uncaught mutants, and I say uncaught, I mean surviving mutants. There's equivalent mutants and then genuine test suite inadequacies. Equivalent mutants basically mutate the code in such a way that the code functionally behaves the exact same before and after the mutant. So I have this kind of example program where I have an if statement and then I mutate the test, but the if statement returns 1 on both branches, so nothing changes about this program. It's the exact same program. So your test cases never have any hope of actually catching that because we didn't change your program at all. So you might kind of be thinking to yourself that maybe equivalent mutants aren't really all that useful, but they kind of actually can have some uses. So this is a snippet of code from a student submission where they have a recursive function that takes in basically a binary tree, a symbol to search for within that binary tree, and a replacement binary tree to put into it. So it should kind of be a pretty simple recursive function. The student has a base case where if they encounter a leaf, they give the leaf. And then they have a couple of different cases for what to recurse on. And the mutator that survived was basically where that red box is. It just deleted that branch from the cond, and the mutant still survived. The tests all passed. What you might notice about that branch is it's testing if the left child is a leaf, and if it is, it provides a leaf for that left child. But what could happen is you could just recurse on the left half of that branch, and it would fall through to the base case anyways. So you don't really need to test if the left and right childs are leafs. You can just let it fall through. And I am going to mention that the test for the right child being a leaf was also an equivalent mutant that the program picked up on. I'm just showing an example of one mutant for right now. So that's kind of an example of how equivalent mutants could kind of help us identify places in our code where maybe we didn't write the most elegant code, or basically we just have redundant code that doesn't actually serve much of a purpose. And then another example of a surviving mutant would be one for a genuine test suite inadequacy. So this is a snippet from one of the open source projects. Basically, this code takes in like an XML timestamp and just tries to parse out the seconds from it. It's got a match statement where the first one tests if it's a well-formed timestamp, basically. And then if it is, it parses out the function, or parses out the seconds. And then it has kind of like a catch-all second case for the match where it just returns false. So this mutator was a match removal where we basically removed the entire functionality of this function. Now, no matter what happens, this function will always return false. So we have clearly broken the code in some way. We've changed the function. But the covering test cases still passed. And that's because this was the test case that was testing for kind of this function, that ran this function at least. And you can kind of see the only check that it does for the timestamps is to check that the data frame has a timestamp column, in which case it does have a timestamp column, just all the values happen to be false. So it's maybe not the most useful test, but it does run the code and it does hit code coverage criteria. And then another example of a test suite inadequacy is this is another open source project. This is for calculating splines between multiple data points. And basically, this is a con to false, so we removed the conditional where it checks basically x and y are equal, so we're on the diagonal of a matrix. So we removed that. this matrix now has a 0 on the diagonal where it should be. Great. So we've definitely changed the functionality of the program once more, and we don't really know, like it definitely is no longer accurately calculating the splines between points. But once again, all the test cases still passed. So we went and found the covering test case, the test case that actually covered that data. And you can kind of see they create the spline, and then they just kind of check that it is a function which returns real numbers, which I believe, we didn't change the generation of the function, we just changed what the function was. So that's another example of kind of how mutation testing can identify test cases which aren't really serving much of a purpose aside from just hitting code coverage metrics. So I'm going to kind of zoom out now and talk about more of the general results. So hopefully I've convinced you now that there is specific cases where mutation testing can be useful. And one of our main goals was, is mutation testing useful for the students? And you can kind of see these are box plots of the mutation scores as assignments go on. And as you move farther to the right, again, the assignments generally get more complex, more difficult, larger programs. We can kind of see a corresponding drop-off in mutation scores of those assignments. So that would kind of indicate that, yes, mutation testing could provide the students with some valuable information because all of these had 100% code coverage, or line coverage, but not all of them have very high mutation scores. And then we wanted a little bit more granular view of kind of what mutants survived for the students. And the first kind of thing that we did is we just looked at which types of mutants survived. And those are we have 3 pretty clear dominating mutants that survived. The remove conditionals and a true, where we insert a true into an and statement. The or to false, where we insert a false into an or statement. And then the conditional true, where we basically replace one of the conditional branches with a true. And I think the reason why the and to true and the or to false are so prevalent is because if I insert a true statement into an and, it doesn't immediately falsify it. So you would need necessarily a bunch of tests to test individually. You're flipping each conditional in the Boolean to protect it against the mutation testing. And then similar idea behind the or to false. Basically inserting a false into an or doesn't immediately falsify it. And then the con to true is a little bit different because you are removing basically, or you're forcing a branch to run. And what I kind of noticed as I manually went through some of these is the students would often have basically a test saying, am I getting malformed data in this function? And then it would error. And the students would say, I'm expecting this code to return an error, but they wouldn't actually check what error they're getting. So their code would error, and their tests would pass, but then they weren't getting the right error that they should have been getting. So the mutants would survive. And just to kind of demonstrate a little bit what I was talking about with the basically and to true, this is just a function that takes in some conditionals. The first 2 tests basically test both possible values that this function could return. And that would probably be what most people consider as good stopping point for tests if you test all possible actions that the function could do. But it wouldn't be mutation adequate because basically if I inserted a true at any point where you're already forcing a true, your tests wouldn't pick it up. So you kind of have to have n+1 tests for the number of conditionals to make it mutation adequate. And students would probably just get pretty bored at that point and it wouldn't really have that much more value to them. So this is kind of an example of maybe mutation testing is a little bit overkill. We don't need that many tests. But yeah, so that's why I think there were so many more of those in the student submissions. And then I also went through the student submissions. I grabbed just kind of a subset of 100 of them, and I looked at basically what equivalent mutants I could find. I ended up finding around 9 of them, mostly in the conditionals to true and the match removal statements. And just because I didn't find more of them in the other ones doesn't mean they don't exist, it's just they're less likely, and I needed a larger size than 100, basically. So now onto the open source projects kind of results. Basically, there was a fair amount of survived mutants, which is good if you're looking for mutation analysis, kind of bad if you're an open source project. And the plot on the right is just the number of survived mutants. So we can kind of see match removal seems to be the dominating mutant that survived here. And I can speculate that's because maybe open source projects tend to be more complex than the student submissions. And for a match case that tests, or for a match that handles a bunch of different kind of conditions, it might be tempting as a programmer to write a test that tests the most general kind of response that that match statement could give you. And then basically you're not really testing the functionality, you're just testing the kind of like the data frame example that we saw, where you're testing the most general response back. So then I kind of wanted to see if there was any way you could predict an open source's mutation score. So the first thing I looked at was the number of stars that it had on GitHub. My thinking was maybe more popular projects have more robust testing, and that was not the case. There was no correlation there. But no. And then I also wanted maybe because the open source projects have variable coverage, maybe coverage could predict mutation score, and that was also not the case. There was no correlation there. So the last thing I looked at was just the size of the project. And this one was actually surprising. It did have a positive correlation, statistically significant. So it seems like larger projects seem to have higher mutation scores, which is surprising just because you would think larger projects would have, yeah. Yeah, it does as well. So that, yeah, I am getting to that, yeah. So there is that. Yeah, so yes. Yeah, but yeah, so yeah, what I was gonna say is, yeah, maybe the larger projects just have more tests, which is inflating these numbers. But I did not look into it any deeper than that. So yeah. And then kind of the most obvious future work that would come out of this would be to implement kind of more mutators into the mutation engine. I really only looked at 2 of them. And we were kind of basing this whole work off of the Java work, where these 2 mutators were the predictors of the rest of them. But we don't really have that information in Racket. So if you could kind of copy over all of the pit mutators into Racket, then you could do that kind of experiment of saying, are these mutators kind of enough for Racket? Or are there other mutators which kind of lend themselves more to a functional programming language? And definitely, I think there are mutators that would exist in Racket that wouldn't necessarily exist in Java, and those might be more useful. As we saw, kind of the match removal was the most likely to survive for open source projects, and that's a specific example of one that exists in Racket but does not exist in Java. So it might just be kind of good to have just other mutators added would be the most obvious future work for this. Oh, and then I also want to mention that for both the open source projects and the student submissions, remove conditionals was the most likely mutator to survive, which kind of aligns with Kazerni's findings in Java. But yeah, so that's kind of all of the stuff that I have for now. Do we have any questions? I think I'm a little quick.
I think there are going to be a lot of questions, starting with Jack.
I've used systems before for mutation testing where I don't configure them. They just leave comments on the code. I write at code review time automatically and like say, hey, we ran a mutation test for you. You didn't have to do anything. And your tests don't cover this case. Gotcha. Can you please give me that for GitHub pull requests? Like just like a little GitHub action I can just stick in my project and it will just start reviewing my pull requests and telling me when I need more mutation coverage.
Yeah, I mean, that could definitely be done, for sure.
I got 2 questions.
Mm-hmm.
The first one is, have you looked at Andrew Tannenbaum's work on Minix and fault injection?
I have not, no.
Okay, because I think he was even before the people you cite.
Gotcha.
And the other one, have you tried to correlate path coverage with your finding of faults?
I have not, no.
Okay. So. Sorry.
No, you're good. No, we just looked at line coverage, basically. Yeah, exactly.
How are the mutants implemented? Are they macros?
Yeah, so they're basically, Lukas Lazarek's mutate library kind of defines a way to define them, and basically they're just kind of match. I basically provide a look for this type of syntax, like a match statement on syntax, and then Lukas's library kind of handles that. I believe it's macros, but
Interesting.
Yeah.
I wonder if it's related to resyntax, actually, which is another library in the ecosystem that Jack works on that rewrites code, it refactors code based on certain rules. I wonder if it could be related.
Gotcha.
Similar idea. There's probably some, I'd like them to do mutation coverage of my rules because they use syntax parse, not match. a mutator, I would like delete this syntax parse branch.
Okay.
Because I don't write that many match statements, but I do write a lot of macros.
Okay. Gotcha. Cool.
Any questions over here? I have another question, or I had one a moment ago and I've forgotten it, so let's take Will.
Hi, William Bowman, University of British Columbia. So you integrated this into a course. You were judging student code. Did you give the students that feedback? And if so, did you see any pedagogical benefit?
No, so we did not give the students feedback. This was done just this last summer. But yeah, the students did not see that feedback. If they did, maybe they could have given us more data, but no.
I was thinking that you've presented this as a way of, as an alternative to coverage, but it almost sounds like it's something that you'd use in addition to coverage. And it could be that it's not just testing your code, it's testing the quality of your test suite. So it's like a test of your tests.
Yeah, exactly.
Do you see that as being one of the main uses of it, to say, hey, how good is your test suite? And
yeah, I think definitely the kind of the main purpose of mutation analysis is test suite adequacy. So it's like a similar metric to code coverage, where code coverage is kind of saying your tests hit these parts of the code, they're X% good, or it hits 90% of your project. You can use that as a metric to judge if your tests are adequate or not. So if you have like a high mutation score, then you can use that as a judgment of adequacy.
Nice.
Jason Heeman, Seton Hall. I was wondering if you found any correlation between the testing forms and the likelihood to have inadequate test suites, or did you look to see if there was any other thing you could correlate between when inadequate test suites actually corresponded with the presence of bugs?
Could you explain what you mean by like test forms?
I mean, specifically in rack unit, the check predicate, check true, check false, as opposed to check equal, et cetera.
Yeah, so I didn't have as much time to look at the open source projects, which would have had more of those. The student submissions all pretty much used just check equal, kind of across the board. That was how students tested their code. Yeah, I didn't have a chance to look at the other ones. And then you had a second part to your question, which was, sorry.
No, it's not fair to ask two questions with one question mark. I was wondering if when you found inadequacies in their test suites, how if you could assess, like, what I want to know is, are these big problems or small problems? Is this a peccadillo, or is this likely predictive of me finding bugs? And I don't know whether you check pull requests against those open source projects, or whether you'd follow up on the inadequate test suites, but is there a way we can track how big a problem this is?
Gotcha, yeah. No, so we did not look at like any pull requests for the open source projects. And additionally, we didn't have any like grading information for the student submissions, just because there's kind of privacy secure concerns with the school. So we didn't have really a way to automatically say, yes, these programs we know to have bugs. If I knew that there was bugs in programs, I would tell people about them. But yeah, we didn't do any sort of that stuff. So, sure.
Really quick.
Jason, in the sampling that we did, I would say that the vast majority of the bugs that we identified were in fact relatively superficial and were not terribly deep. That's based on just a kind of a quick survey of the ones that we saw. Yeah.
All right, I think that's all the time we have, but thank you so much. Please turn it into a tool. Let's give it up for Charlie.